Okay, so this is uh, the second part of chapter 2, the approximation of roots of nonlinear, transcendental, and polynomial functions. So in the first part, we discussed some types of bracketing method. In this part, in this section, we will be discussing the other types, the non-bracketing, or we sometimes call them the open methods. In the first section, in the bracketing methods, uh, we we locate the roots within an interval that is prescribed from a lower and upper bound. Then after that, we repeat the applications of these methods, and then the answers when we do iteration, the our approximation will always be converging or go closer to the true value. So those methods are said to be convergent because they are converging with the true values. In contrast, the open methods or the non-bracketing methods is different because we don't start with the interval. We only start with a single starting value. Sometimes two starting values, but not necessarily uh, bracketing the root. And this type of methods are not convergent, not always converging with the true value, and they sometimes diverge or move away from the true value or the true root as the computation progresses. However, when the open methods converge or go closer to the true value, usually the iteration is much lesser, meaning it's so much more quickly than the bracketing method. And we will be discussing from our syllabus, we just discussed, we will be discussing two types of non-bracketing or open methods, the Newton-Raphson and the second method. Perhaps the most widely used of all root locating formulas is the Newton-Raphson. So the first one, so here we will be talking about the Newton-Raphson or simply Newton's method. Then lastly, we will also talk about the second one, the second method. So first, uh, Newton-Raphson method. So for Newton-Raphson method, so this is the widely used root locating formulas. We need to indicate an initial guess for the root, and we will try to solve the second one, the next iteration, by using Newton's method. So the Newton-Raphson method, Newton-Raphson method can be derived through the concept of a tangent line to a certain curve or a function. So if we remember, so this is the concept. So if we have here a certain function, let's say so here we have a function that goes into that direction. Then tangent line means if I get point somewhere here, Then if I draw a tangent line to that point, and the slope of that curve is actually the same as the slope of the tangent line. So this will be our tangent line here. And how do we solve for the slope of this tangent line? So let's say this point here, let the function to be fy equals f of x. So this point here, let's say this is our initial guess. Actually, this is our initial guess. Let's call it x0. And the coordinate of this point now will be x0, and the value for the y is f of x0. So that is the point where the curve y equals f of x and the tangent line intersects. And then we project this one. We project the tangent line up to the x-axis. So there will be another point here between the intersection between the tangent line and the x-axis. So let's call this will be our next approximation for the root. So we will call it x1. This will be x1, and the value for y here is, because it intersects with the x-axis, then this will be 0. Then to derive the formula for a NewtonRaphson method, we simply solve for the slope of the tangent line. So remember, the slope of the tangent line, m tangent, from your calculus, this is just equal to the derivative of y with respect to x, or this is simply f of prime x. And we also know that the slope of a tangent line from analytic geometry, this is rise over run. So this is y2 minus y1 all over x2 minus x1. So if you're given 2 points, we can solve for the slope by solving or by using this formula. We have 2 points here, x0, f of x0, x1, and 0. So we can substitute that one to solve for the slope of the tangent line. And this will be equal to dy dx, or simply f prime x. So what will be our y2? Our y2, we can set our y2 to be equal to 0. So 0 minus, so the y1 will be f of x0 on the other point. Then we divide this one with x2 minus x1. Our x2 here is x1, this point. Then we subtract x0, and this will be equal to f prime of x. Then what we want to solve here is our new approximation. We need to know our new approximation, and our new approximation will be x1. Our initial approximation is x0. So solving for x1, so this will be negative of f x0 equals f of prime x multiplied by x1 minus x0. So what we want is x1. So we can distribute that to negative f of x0 equals x1 times f prime x minus x0 f prime x. Then retaining x1 f prime x, then putting negative x0 f prime x to the other side, that will become positive 0 f prime x. And I will retain this one minus f of x0. Then dividing both sides with f prime x. So x1 now will be equal to x0 f prime x minus f of x0 divided by f prime x. So this will cancel out here. So x1 now will be equal to x0 minus f of x0 all over f of f prime x. So this will be the value of our new approximation. But in general, instead of using x1, we can just put here xn plus 1. So this is in general. And x0 now, instead of x0, we can start at any point you want, xn minus f of x0, which is xn, divided by f of prime x. xn. This will be x. This is x0. So this will be our general formula for the approximation of the new root and using the Newton-Raphson method. Now let's try to solve our previous example using Newton-Raphson. So our previous example was f of x equals x cubed minus 0.3. So we already know the true value of this one. We already solved this one before, and our true value is up to 4 significant figures. X is equal to 0.69 or 6694. This is our true value. We solved this one before, or you can also use your calculator to solve this one. We choose this example because we know the true value, so that we can compare with our approximation. Later on, we can try to solve much harder problems. So using Newton-Raphson method, so we need to first choose our initial guess, our x0. So that's the first step. What is our initial guess? So we know that it's 0.6694. So we can put our initial guess to be equal to 1. We cannot use 0 as our initial guess. Why? Because if you look at the equation, here we have f prime xn. So when these become 0, then our calculation will be a number divided by 0 is determining, and we cannot do that. So we cannot just use x0 as equal to 1 instead of x0 equals 0. But you can also choose 0 if you can check, as long as the denominator of the function, or the f of prime x and f of prime x will not be equal to 0, then that initial guess will be right. But here, if we use 0, our f of prime x will become 0. So we cannot use 0. So the next one is 1. So we will be using 1 instead of 0. So the technique is we solve for the next one. So x0 is our initial approximation. And if we solve the approximate error, we don't know yet our approximate error, but we can solve for the true error. The true error will be equal to 0.6694 minus 1 divided by 0.6694. So that's the true error, but we don't know the true error in actual problem solving. So we can just go to the second iteration, or the first iteration. So we now solve for x1. So what will be our x1? So from our formula, x1 is equal to x0 minus f of x0 divided by f prime x. So our n here is equal to 1, or 0. So n plus 1 is equal to 1. So here, this will be x0 and minus f of x0 all over f of prime x0. Okay, so then we substitute what is x0. x0 is 1. Then what is f of x0? We just substitute 1 here. So our equation will be 1 cubed minus 0.3 all over f of prime x0. So we don't know yet f of prime. So we need to determine f of prime. So what's the derivative of x cubed minus 0.3? So based from our rule, so this will be 3x3 minus 1, so 3x squared. Derivative of a constant is always equal to 0. So this will be f of prime, 3x squared. Then we put here 3x squared. So this will be 3 times f of x 0, f of prime x 0 is 1, so 1 squared. Then solve for x of 1. What will be our new approximation? So we can use your calculator, you can program your calculator using our formula. So our formula will be, I will just write here, x0 minus f of x0 x0 cubed minus 0.3 divided by 3 times x0 squared for any value for x. So this will be our general formula. So here I will put that in my calculator, then just calculate for the value of x. So shift alpha x, then minus alpha x cubed, then minus 0.3 all over 3 times alpha x cubed. Then you just press calc. After inputting this equation, you just press calc, and it will ask you what should be the value for x. So our value for x here is x0, which is equal to 1. So we just put here 1, then press equals. Then this will be our answer. So it will be equal to 0.76667. 0.76667. 1, 2, 3, 4, 5. The next. So after that, don't press AC of your calculator or on, so that it will not delete our previous calculation. So we can go to the next iteration, x2. So solving for our new approximation, this will be equal to, instead of x0, this will now be x1 minus f of x1 all over f of prime x1. Or this is, our x1 is here 0.76667 minus that answer 0.7667 cube minus 0.3 all over 3 times 0.76667 squared. Then we go back again to our calculator and solve that. So instead of pressing AC, we just press again cut, then ask the value for x. And our previous value for x was 0.7667. Instead of typing that, you can just press answer here, ANS, so that our input will be the input of the previous calculation, and press equals. So this will be our new iteration, 0.6552. Then we go again, x3. So for x3, this will be, instead of x1, it will be x2. I'll just directly put the values now. You don't need to write them every iteration. So you can just directly put the values. This will be 0.6552. This is x2, the previous approximation, minus that value, 0.6552 cube minus 0.3 all over 3 times 0.6552 squared. Then calculate again, go our calculator. Then we have a correction on the previous value. It should not be 0.6552, it should be 0.6812. So this is wrong. It should be 0.6812. So all of this will be 0.6812. It doesn't matter. Okay, 0.6812 minus 0.6812 cube all over 0.6812 squared. Then we press it again, or calculator, calc, then answer. and equals. So this will be our new value, 0.6696. 0.6696. Then we go for the fourth iteration, so this will be 0.6696 minus 0.6696 cube minus 0.3 divided by 3 times 0.6696 squared. The answer will be, so press calc. Then, so our value, new value now, so calc again. Then answer equals. So this will be our new value, 0.6694. 0.6694. And if you observe, we already reach our true value here, which is 0.6694 also. So we can see that NewtonRaphson really is a very quick calculation. It needed lesser iteration, and the calculation is very simple. The only drawback of this technique or method is finding the derivative of the function. So the function is difficult to take the derivative, and it's also much harder for us to implement in Octave or MATLAB because we need another function to find the derivative of our function. But in Octave, there's a certain function, built-in function that can solve for the derivative of a given function. And we can use that, but it's not that easy to use because we need to install some packages, and we will discuss that in our laboratory later on. So in conclusion, NewtonRaphson is really a quick solution, quick method to solve for the approximation of the root. The drawback is finding the derivative, and sometimes there's some examples that NewtonRaphson is not practical to use, or it uses more iterations, and this is when the function has a the root that we are finding is near a point of inflection, meaning there's a maximum and minimum around that root. So if that's the case, sometimes the NewtonRaphson method will not give us the correct answer. So that's the drawback of NewtonRaphson. And let's try to solve another one, and let's make it in tabular method. Let's try to solve this one. F of x equals negative ln x minus x cubed. Or sometimes the problem is not in function notation. It's just L. Sometimes it's in this kind of notation. Ln x equals positive x cubed. Then the problem asks, what is the value of x? This is the problem. What's the value of x? So first, we need to go into function notation, and then after that, we equate it to 0 and find the root. So find the root of this one using NewtonRaphson method, and let us use or make it in tabular method. So what are the variables that we will be using? So first, the n value. Then we have xn. Then we have f of xn. Then we have f of prime xn. So this is the variables that we will be needing in our table for in NewtonRaphson method. So we can also include the approximate error, the last part, epsilon a %. can indicate our number of significant figure, or we can just put any value that we want. Let's say our pre-specified is 0.005%, meaning this is for significant figure. So let's do this. What will be our initial guess? To minimize our calculation, it's a good practice to plot first our function so that we can approximate the initial guess closer to the value that we want, the root that we want. And here, our initial guess, because I know the root of this one, so we can use x equals 1. So our initial guess, x0 is equal to x equals 1. So 0, so meaning n equals 0, x0. So what will be x0? x0 will be equal to 1. So our initial guess is 1, just like the previous example. Then solve for f of xn. Again, this is our equation here. So you can again use your calculator to put that one in your calculator. Alpha or negative alpha or ln alpha x, then minus alpha x cube. Then press calc. So our initial value is 1 equals 0. So our f of xn will be equal to negative 1. How about f prime x? What will be our f prime x? So we always forgot f prime x. So what's the derivative of negative ln x minus x cubed? What's the derivative of ln x? F of prime x. Derivative of ln x is just equal to 1 over x. Remember? So this will be negative 1 over x. Then derivative of x cubed, it's just negative 3x, 3 minus 1. So that's a squared. So this will be f of prime x. Then what will be our equation? So it's a good practice to write first the equation. I forgot it again. Let's first write the equation here. Let's just put here epsilon s equals 0.005%. Then our equation now, xn will be equal to plus 1 xn minus f of x. Remember, f of x is negative ln x n minus xn cube all over f of prime x, which is this one. So minus negative 1 over xn minus 3xn squared. So this will be our equation, our guiding equation, solving this function. So we will put this one in our calculator. So here, alpha x minus negative ln of alpha x, then minus alpha x cube, then all over negative 1 over xn, so negative 1 over alpha x, then minus 3 times alpha x squared. So this will be our value. Then next, or because we are using the table, we can just rather indicate the values of x prime and f of xn. So we need to compute it individually because it's in the table instead of doing it directly. So we just take first f of xn, then second f of prime x. squared. Then cog our xn is 1. So this be 1 equals, so that is our f of prime xn, negative 4. Then we go to the next iteration. So we have now n equals 1. So what will be our new xn? Our new xn will be our calculated here will be equal to 1 minus 1 minus f of xn, negative 1, all over f of prime xn, negative 4. And this will be equal to 3/4 or 0.75. Our new value for x now is 0.75. Then what will be our f of xn and f prime of xn? We just use this one. Negative or positive 0.75. Negative ln of 0.75. Or we just write the equation. Then just substitute the values. We'll be using this again, so it's good to write the equation and just press replay. So then this will be 0.75 equals. So this will be f of xn, negative 0.134192.9. Then for f of prime xn, just replay this one, then calc and 0.7, and that will be our value for f of prime xn. So negative 3.0208333. Then we can solve for the approximate error. Alpha x negative 0.75 minus 1 divided by 0.75. So absolute value times 100. So this is our approximate error, 33.33. Absolute value, which is absolute value, 33%. Next, number 2. So when n is equal to 2, so x2, we go again to our calculator. We input the values here. So xn, our last value for xn, 0.75, minus f of prime or f of xn, and that is negative 0.134192.9 all over f prime x, negative 3.0208333. So this will be our new value for our approximation, 0.7055775. Then what will be f of xn? F of xn will be this one. So calc, then 0.7055775 equals negative 2.5 times 10 to the negative 3, or so this is around negative 0.0025258. Then for f of prime, this one, card. It's the same. Equals. So it will be negative 2.9, negative 2.9107,976. And if you calculate for the approximate error, 0.7055775 minus 0.75 divided by 0.7055775 equals minus 6%. The next 3 for the third value. So what will be our xn? Our xn now will be equal to 0.70557775 minus f of fx negative 0.0025258 all over negative 2.9107,976 equals. So this will be our new value 0.704 0.70470,976 or let's make this one 0.98. And if we solve for the approximate error before we go through, we just check first 0.7047098 minus 0.7055775 times 100. It's 0.12%. 0.12%. So we need still to continue our iteration here. So next we need to solve for f of xn and f of x prime. So just click replay. 0.7047098. So this will be our new value for f of x n, negative 9.01 times 10 to the negative 7. So it's really close to 0. F of x n now will be really close to 0. So this is around negative 9 point something times 10 to the negative 7. 9.01009 times 10 to the negative 7. And for f of prime x, this will be negative 1 over x. Negative 1 divided by 0.704 47098, then minus 3 times 0.7047098 squared. So this will be negative 2.990888715. Then we go to the fourth one. So what will be our new value for our xn now? So again, we use our formula xn. Our previous value 0.7047098 7098 minus f of x divided by f of prime x. F of x is negative 9.01009 times 10 to the negative 7 all over f of x prime and negative 2.90888715 equals, so this will be our new value, 0.70470903. Then if you calculate for the approximate error will be 0.70470903 minus 0.704709.8 divided by 0.70470903 times 100. So this will be our new approximate error. So this will be 0.000109. So it's now less than 0.005. 1.0926 times 10 to the negative 4%. So we can now stop our criterion, our iteration. So our value now for x, our root is equal to 0.70470903. We can make this our solution shorter by simply decreasing the number of decimal places that we want. But here we specify that it's 0.005%. That's equivalent to 4 significant figures. So 1, 2, 3, 4. Or we can just make it up to 4 decimal places. So if it's 4 significant figure, from here to here, this is very accurate. Now, the Newton-Raphson method is a very accurate method because every iteration here, the error, the true error, is approximately equal to the square of the before the previous iteration. So it doubles. So here, actually we can stop up to the second iteration or the n equals 2. This is already an accurate if you want up to 4 significant figure because it's 0.705 because our total value is 0.7047. So if we round up that off to 3 decimal places, then it's 0.705. So there's an allowance again of 2 or more number of significant figure. So this is a Newton-Raphson method. So it's a very powerful method in approximating the root of a nonlinear, transcendental, and polynomial functions. So the next one will be about second method. So we end this discussion here and we go to the next one.